Okay, next, after volume flux balance and momentum flux balance, we derive buoyancy flux balance. Okay, and for buoyancy flux balance, we take a little different approach. Instead of considering in a small element in vertical direction, we first define buoyancy for a particular z axis or z location. Okay, so let's say this is the plume, and we consider this is the slice we are talking about. So that will look something like this from the top, right? And here we consider one small element. Okay, so in this case, this is the side view and this one is the top view. Okay, and here this small length scale is dr, and this is small r, and this is capital R. Okay, and this small element has w, which is a function of rz, and also it has g prime, which is a function of rz. Okay, and what is g prime again? That is rho a minus rho p by rho infinity, where rho infinity is the reference density multiplied with g. Okay, so as we have seen previously, the definition of buoyancy flux can be actually for this particular slice at location z can be given as 2 pi r dr, or let's put that this side. So g prime times w 2 pi r dr. Okay, and that gives you the total buoyancy if you integrate it from 0 to infinity, right? So 0 to infinity, where this one is the volume flux, right? Volume flux through that small element, and if you multiply that with reduced gravity, that gives you the buoyancy flux. Okay, so and here this is the buoyancy flux. Okay, which is actually at any z, and that's why we can write this as a function of z, something like this. Okay, where this here is z. All right, so now what we do, we define g prime. So p here should be, we can take 2 pi outside, and w remains there, and g prime becomes rho a minus rho p divided by rho infinity times g r dr. Okay, so this is b at any location z. And what we are trying to find here, we are trying to find a governing equation or a differential equation that tells us how b is changing with space in z, right? As we did here for buoyancy momentum flux, where we've tried to find the rate of change of momentum with height. Likewise, we did already for volume flux. We tried to find the rate of change of volume with respect to height, and same thing we have to do now for buoyancy. So in this case, as I said, we are already using a different approach, and that's why we will simply differentiate dB by dz, because this is something we are trying to find, and 2 pi being constant simply comes out. So this actually is going from 0 to infinity. W rho a minus rho p by rho infinity r dr. Okay, and we know that z is an independent axis. It is independent of r, and that's why d by dz can be taken inside. Okay, and that's why we can write it as d by dz, where we take rho infinity outside because that's a constant, and this becomes d by dz rho a minus d by dz w rho p and r dr. And why I'm using the partial derivative? Uh, uh, because these are both dependent on r and z. Because now we have taken the differential inside, we need to convert this from ordinary differential to partial differential equation. Okay, so what do we do now? In this case, we expand this equation first. So let's do it step by step. So dB by dz is equal to 2 pi by rho infinity, and d by dz w rho a r dr minus 2 pi by rho infinity 0 to infinity d by dz w rho p r dr. All right, so dB by dz becomes 2 pi by rho infinity d rho a by dz w r dr. There should be w here, plus rho a dw by dz r dr 0 to infinity minus 2 pi by rho infinity. This one will leave as it is for now, rho p r dr. Okay, so this is where the last term here is not very clear, but that is dr. Okay, and what do you see here is, we know that rho a is not a function of r, right? And that is where d rho a by dz can be taken out, and in fact that can simply be written as a ordinary differential rather than partial differential. Okay, and likewise rho is also not a function of r, so rho a can also be taken out, right? So this equation basically becomes dB by dz 2 pi rho infinity d rho a by dz 0 to infinity w r dr plus rho a 2 pi by rho infinity dw by dz r dr 0 to infinity minus 2 pi by rho infinity 0 to infinity d by dz w rho p r dr. Okay, so this is what we get. And another simplification we can do here is if we put 2 pi inside the derivative. So let's, in this equation we can do that. We will simply remove this part, that becomes 1, and I will move this little bit here, and this also goes here. So now this becomes w 2 pi r dr. Okay, so 2 pi r dr w. So now if you look at this equation, you can simply say that this is actually equal to the volume flux. right? This is the volume flux, and that must be equal to pi r square w bar, right? That is the volume flux, and if you integrate it from 0 to infinity, this is eventually what you get, and that's why we can simply replace the first term with pi r square w bar. And then for second and third terms, we are going to use two different equations here. One is equation and one is assumption. So equation is continuity equation in axisymmetric geometry. So remember that we have already studied continuity equation and Navier-Stokes equation, but they were in rectilinear geometry. But this equation in particular, I am writing for axisymmetric geometry, because Plume we are considering to be axisymmetric in nature, or these also called radial geometry, right? And here we write the equation as 1 over r d by dr rho r u plus 1 over r d by d theta rho u theta plus d by dz rho w is equal to 0. Okay, so this is the continuity equation in axisymmetric geometry, right? In the differential form, right? And what we do here, we already know that the angular component is 0. Angular component is 0, and that is why u theta is simply 0, and also d by d theta is 0. So middle term can simply be neglected, and this equation becomes 1 over d by dr ru d by dz rho w is equal to 0. And what do we get from here? So this d by dz rho w is equal to minus 1 by r d by dr rho r u. Okay, so this is what we get, and this can actually be replaced, can be put in the last term of the above equation. Okay, and here we are also considering Boussinesq approximation. Okay, and if you remember that, if you consider Boussinesq approximation, you neglect the density variation within a particular equation, except when it is multiplied with the density, the gravity, right? And that is why, because continuity equation with Boussinesq approximation assumes rho is a constant, and that is why this equation can also be written as, here we assume rho is constant, or variation of rho is insignificant. Okay, and that is why this equation what we have written above can also be written as 1 by r d by dr ru plus d by dz w is equal to 0. Okay, so we are simply assuming that rho comes out because rho is a constant, and that goes the other side, that becomes 0. So this actually gives us dw by dz as minus 1 by r d by dr ru. Okay, so this is we get again from continuity equation, but by applying Boussinesq approximation. So we have got these two terms, and we are going to use these two terms in this equation that we have written above. Okay, so we can write that equation again as dB by dz, where this term, the first term, can now be written as pi r square w bar. So I'll simply write pi r square w bar by rho infinity. and that is d rho a by dz. Okay, and then in the second term we can write 2 pi rho a by rho infinity 0 to infinity, and here dw by dz becomes minus 1 by r d by dr ru r dr. Okay, and the last term becomes minus 2 pi over rho infinity 0 to infinity, and here we have d by dz w rho p, so w rho p becomes minus 1 by r d by dr rho ru r dr. And here I am not writing particularly rho p, because when you write continuity equation you write it as density, because this is continuous, it can be applied at all points, and that's why you don't want to define rho p versus rho a, you just write it as rho, not rho p or rho a. Okay, and now we can cancel some of the terms here. So this cancels with that one, this cancels with that one, and what do we get here? dB by dz is equal to pi r square w bar by rho infinity d rho a by dz plus 2 pi by rho infinity. I can take 2 pi by rho infinity outside, so this becomes rho a. And here we have, I guess there is one missing. Okay, so that one should, okay, so eventually it will become positive, minus 0 to infinity d by dr ru dr plus 0 to infinity d by dr r rho ru dr. Okay, so now you can see this is both differential and integral, and that's why we can simply pull them outside, and this will become pi r square w bar by rho infinity d rho a by dz plus 2 pi by rho a, and this becomes minus rho a r u it from 0 to infinity plus rho r u from 0 to infinity. Okay, so now either we can simply assume that r becomes u becomes 0 at infinity, and r is already 0 at the limit 0, or we can replace infinity with r, because we are assuming that plume exists from 0 to r, right? So in either case this will become dB by dz pi r square w bar by rho infinity d rho a by dz 2 pi by rho a, this will become minus rho a r u, and plus that will become rho a r u. So this actually, okay, so we assume that at r equal to r or at r equal to infinity, your rho is equal to rho a. Okay, and that is why you replace rho with rho a, and that gives you this particular equation, and eventually this both of them simply cancel out. So remember, this is, we are able to do it because we applied Boussinesq approximation, otherwise we would not be able to do it. And there are many other ways to do it. You can also derive the same equation by considering solute transport equation rather than applying Boussinesq approximation. But eventually you will end up with this particular equation that we have written here. So this becomes dB by dz is equal to pi r square w bar over rho infinity d rho a by dz. And remember that B in its bulk form can simply be written as, so that is q into g prime bar, that will be pi r square w bar into g prime bar, right? So this is what we know about the buoyancy flux, that is volume flux into G prime bar, where here obviously we are assuming R, W bar and G prime bar as the function of Z. And that is why if we replace B with this term, that becomes pi R square W bar by rho infinity d rho a by dz, and here we cancel pi, so that becomes d by dz R square W bar G prime bar, and that becomes R square W bar rho infinity and d rho a by dz. Okay, and there is a G term that we are missing here. So the G term is missing, and that is actually missing from the first step, where you see we had a G here, but we forgot to put that in the next step. So that G will simply come here, and this will remain in all equations from there until all the next steps. Okay, so or we can do something is we just write 1 over G here, so that we don't have to write in the right hand side. Okay, so this becomes 1 over G, this is 1 over G, and now we will pull the G to the other side. So that was missing, and here we can write this as G. Okay, so all right, so what do you see here in this equation? This particular term, this has one specific name, and that is called the stratification frequency. So this is usually written as minus n square, or n square is equal to minus G by rho infinity d rho a by dz, is known as the stratification frequency. And this is a term which is usually used by people working in stratified medium. When the ambient density is changing in space, this is how you tell how stratified the medium is, or in what pattern the stratification is occurring. Okay, and this is generally given with a sign negative, because we consider that your density is changing in vertical direction, right? Because rho a is decreasing with z, not increasing with z, right? And z is going in upward direction, and that is why, to account for that decrease in density, we use negative sign. And if you look at the, if you want to find what is the unit or dimension of n square, right, we can quickly do rho a by z. So that will be, so for rho a it will simply cancel, and G is meter per second square, and Z is already in meter, so this cancels. So basically 1 over second square, and that is why your n is 1 over per second. Okay, and that's why this is called frequency, stratification frequency, because its unit is 1 over second, or per second. Okay. All right, and what should be n for an unstratified medium? That should be 0, right? Because your rho ambient or ambient density is not changing with the height, that remains constant, and that is why d rho a by dz is 0. That means your n square is 0 for unstratified medium, but in case of stratified medium, this is not 0. All right, and that is why this equation can be written as d r square w bar by g prime bar over dz is equal to minus n square R square W bar. Okay, in this equation, let's call it equation C, and this is the buoyancy flux balance. Okay,